All right, go ahead, please.
Okay, thanks. So first of all, it's a great honor to present at these Mondays of Memory meetings. I remember going to them myself, so thank you for inviting me. Today, I'm going to be presenting a work of ours by myself, Ronnie, who's in the audience, and Shachar Kotinsky, called PyPIM. And the goal of PyPIM is to integrate processing and memory like we saw with Joel's presentation, but more focused on resistors, all the way from very high-level architecture, high-level Python tensors that you would used to see in stuff like PyTorch, NumPy, all the way down to the microarchitecture that we're going to have in the architecture. So without further ado, let's begin the presentation. The background, I'm sure you're all familiar. We're focusing on processing memory architectures. So instead of only having a read-write interface that can cause a memory wall, we want to focus on adding support for operations within the memory. And this is typically best used for SIMD operations because then you send a single instruction and it covers a large number of data elements. And in order to get to this model of processing a memory, we're going to take a different approach that's based on memristors. Memristors, what we see here on the left, are essentially two terminal resistive devices. So they're very similar to a regular resistor. They follow Ohm's law, with the major difference being that a strong current in one direction will increase the resistance, and a strong current in a different direction will decrease the resistance. So basically, we can think of this as like a resistor where a small voltage just behaves like a regular resistor, but a large current can change the resistance itself. And that means we can first of all use it to just store information, because we can define high resistance is going to be a logical 0, low resistance is going to be a logical 1, and now we can store information with that strong current and measure the information by sensing the resistance of the resistor. But the more interesting part is that we can also use the same physical device not only to build the memory, but also to perform logic. And that's what we see here on the right. It's a logic gate called the magic gate. And essentially what happens is if you take 3 resistors, connect them according to this circuit that we see here, then by applying 2 fixed voltages, apply 2 very fixed voltages at the top and the bottom, say 1 volt and 0 volt, then we'll get that the state of the bottom resistor, with the state being the resistance, will become the NOR of the 2 states of the 2 top resistors. And this follows because if at least one of the top resistors has low resistance, then that'll mean that a strong current will flow through the bottom resistor. And what we have here is essentially a single physical device that's able on one hand to store information, on the other hand to also perform logic on its own. So we're going to try and take it and build a larger memory out of it, with the first step being to take this memristor and integrate it in crossbar arrays. And then we find that the same logic circuit that we had a second ago with the NOR gate exists within every single row of the crossbar array. If you apply 3 fixed voltages on 3 bit lines, what we see here is we're applying 3 voltages on the first, second, and fourth bit line, then what we get is that in each row of the crossbar, we're going to have the exact same circuit that we saw on the left. And that means that by applying these 3 fixed bit line voltages, we're getting that all of the rows are doing the computation at the same time. And we can think of this in a more abstract model, which is that our crossbar is a binary matrix of information, and we can do column operations. You take 2 arbitrary columns, perform a NOR gate, store in a different column. Now, I've gone through this a bit quickly because we can get to the same abstract model from other architectures, like what we just discussed, which was DRAM architectures. From DRAM, we can use works such as Ambit in order to perform similar operations, albeit there it's on rows instead of columns. So just think of it transposed. But again, the same model of you can perform these bitwise operations in parallel. And we're going to take this model and try to first of all define what are the different parallelisms we have. So the first, we already said, we can do these operations in parallel on rows. Turns out that if you are with memristors, you can usually do both directions. You can both do parallel operations on columns and parallel operations on rows with the same crossbar. So that's our first parallelism. We can operate across the entire row or column in O at a time. Our second parallelism, we're going to dive into it a bit more later on, but essentially it asks what happens if I dynamically split this crossbar array into different parts. Why? Because in the previous version, yes, we could work across all the rows at the same time, but each row could only do a single NOR gate per cycle. Here, we're trying to split that row into different units so that each unit can perform a single NOR gate per cycle, and that'll increase our parallelism even more. And then lastly, we have crossbar parallelism. You take this, you repeat it for all the crossbars that you have consisting of the entire memory of your chip, and then you're able to broadcast operations to multiple crossbars when you wish. Now, these are the 3 different parallelisms that already exist from a theoretical perspective for these digital PIM architectures. What are the 3 challenges that we're coming to solve here? So the first challenge is going to be array periphery. And this challenge exacerbates significantly once you look at partition operations, because we have this very complex set of operations that we need to support because of partitions. And we'll dive into exactly how we can both encode those operations into an operation format, and then also support periphery that's able to decode that efficiently without needing too much area overhead. The second question is the abstraction. How can we design different types of these chips to meet the same models so that we can have, for example, different manufacturers following the same concept and use libraries that are built on top of that? And also programmability. We're going to try to take it all the way up to a Python level interface so that you do not need to be aware of the very low level operations that are happening inside the crossbar when you're programming an application for these chips. And lastly, we need some way to start working with these architectures before they're going to be ready fully from the experimental perspective. And for that, we're developing a simulation architecture which models the entire chip in a GPU and enables you to perform chip level operations and already have today the ability to work with that library and debug and implement it in real time. So without further ado, the goal of PyPIM is to be able to start from a very high level Python application, like we see here on the left, where for those of you who are familiar with NumPy or PyTorch, they are the Python interfaces for CPUs and GPUs in Python. And their overall idea is to give you some interface that on the one hand is very simple to use in Python, on the other hand is very optimized. And the operations themselves happen either in optimized CPU or GPU code. So here what we see on the left is we have this high-level Python application. You import us as a library, and then you're able to do operations such as allocating a tensor. So here you're saying, give me 2 tensors or 2 lists of size 1 million elements each. You can then write to these tensors. You can perform operations on them. So like when you do A times B plus A, it's going to convert that all the way down to these operations that we're doing in PIM. And then you can also do more complex operations, such as what we see here on the bottom. Take a vector, return all the even indexed values of that vector. That's what we see with the brackets and then the colons and 2. So get all the even indexed values of that tensor and then perform reduction sum on them. And that's going to convert to a higher level algorithm. So we take this high level Python application, and the first step is it meets our Python library. This is the same library you import with import PyPIM. And the idea here is it's a general library that's going to include all of the general routines that are going to be applicable to many different architectures. So for example, we have memory management here. We have general purpose algorithms like reduction, like sorting, etc. And this is going to be our first high level library. Then we're going to add another library that's going to be in the CPU, and this is going to be our driver. Now, the main difference between the driver and the development library is that the driver is specific to a specific architecture and chip and manufacturer. The library is going to be generic so that we can develop lots of different algorithms, if it's reduction, sorting, etc., and then apply them to many different architectures. And to that end, what we do is we construct an instruction set architecture, an ISA, that is going to be this interface between the high-level Python library and the C++ static library. So that means that as long as you match this interface on both ends, you're going to be able to interchange the driver and keep the same development library and all the applications that are built on top of that. Then this development library is going to generate operations according to our microarchitecture. The microarchitecture is already very low-level operations that are being sent to the crossbar arrays to perform the logic. And it's being sent from the driver all the way over to the PIM chip on one hand. Another option is until we have an experimental PIM chip at scale that we can test this on, we developed, as I mentioned earlier, a simulator for the entire PIM chip, which works exactly according to the microarchitecture. It decodes the operations that you're sending in binary to the microarchitecture, and then performs both an entire chip simulation for an entire scale of the chip, and is accelerated by GPUs so they can test more complex algorithms, not just simple operations. So without further ado, we're going to start, but in reverse. So let's start with the microarchitecture. Here we have our microarchitecture format. We're not going to dive into the exact encodings of each operation, but we will highlight what is interesting, which is, first of all, this is going to be our only interface between the PIM and the CPU, which means it's also going to support regular read-write operations. we wanted to support not only apply an operation across all the rows and all the crossbars, we want some ability to mask these operations with operations that are going to select certain rows or crossbars. And we want to support very complex partition logic that has a very high degree of flexibility. So let's start for a second with mask and read write. And for that, we're going to take a look at how are we going to represent information in this crossbar. So what I have here on the right is a crossbar that's split into partitions. Again, we'll dive into partitions in a second in terms of what their ability is to compute logic. But for now, I'm going to take a crossbar, say 1,000 by 1,000, and I'm going to split it into 32 crossbars, 1,000 by 32. That's what we see here for each one of them. And they're going to be connected to each other with these wires in between. Now, when I have a 32-bit number that I want to store in this crossbar, I'm going to store it in a strided fashion. So I take this number, for example, at the beginning, 70111, and I'm going to split the bits according to the different partitions. Each partition has a single bit from each number that's stored there. And this makes it easier, for example, to perform read-write operations because you multiplex these columns from each partition and then send it to a sense amplifier. So it also works well with our read-write interface. The next thing we're going to do is take this partition architecture and see what are the different logic operations we want to support and how can we encode that with a very compressed instruction architecture. So for that, let's dive into what is partition parallelism. As I said, take a crossbar, split it into many different partitions. Now we have these switches that connect each one of the different partitions, and we can decide dynamically when to connect and disconnect. So for example, if I decide to connect all the switches, essentially I get a crossbar that's equivalent to a regular crossbar. It's 1,000 by 1,000. Everything is connected in terms of the word lines. And that means I have high flexibility in terms of I can choose what 3 columns to perform the operation on, but I'm going to have low parallelism because within each row, I only perform a single NOR operation per cycle. I can go the exact opposite and say I want full parallelism. Full parallelism means that I'm going to have all of these switches open. Each one of the partitions is going to be as if it's a smaller crossbar of 32 by 1,000. And that means that I can perform a NOR column operation in each one of them in parallel. So you can think of this as saying each row is not performing a single gate per cycle, but each row is performing 32 gates per cycle. And this is going to give us much higher parallelism, but at the cost of flexibility. Because now we can't choose arbitrarily where are the 2 inputs and output for each operation. We have to constrain it to these partitions. You have to have all of your inputs and outputs in the same partition for this to work. Now, an interesting case is what happens when you do semi-parallelism. You connect some partitions, you disconnect others. And this is going to give us a trade-off between the 2 of them, and it's going to make it possible to both have moderate parallelism and also have some flexibility. You're not going to be constrained to within a single partition. Let's see how we can use this. So let's say that we have all these 8 partitions, and we have a single bit stored in each partition, and we want to shift it all to the right. We want partition I to get the bit from partition I minus 1. If we were constrained to a regular crossbar that doesn't have partitions, that would take O of n operations, because you need to copy from each column to each column. Instead, if we have the shift technique, if we have partitions, then we can do this shift technique, which is first copy from all of the even indices to odd indices partitions. What we see here is that in between some partitions, we connect the switches, and between others, we disconnect, and then we alternate. And then we have another operation which switches which ones are connected and disconnected, and then does that shift as well. So this way, with 2 cycles, and then choosing each time when to connect and disconnect the switches, we're able to do this shift technique very efficiently. And we have a previous work that did not only this shift technique, but expanded it to other techniques like broadcast, reduce, prefix techniques that are very useful in the algorithms they build on top of the MIM PIM chips, and which are all based on these adaptions of when to connect and disconnect the partitions. All of it is based on semi-parallelism. So now that's the theoretical background for what we were trying to do with partitions, but then the question comes, how do we implement that in the periphery? And for that, let's take a look at a standard array periphery. And by standard, I mean a MIM PIM crossbar, but before we added partitions. So this standard crossbar, what does it need to support? It needs to support choosing 3 columns arbitrarily, and then applying the corresponding voltages. You need to apply 2 input voltages and 1 output voltage. And how can we do that? We take this column decoder. It's going to consist of 3 decoders inside. Each one of them gets an address of log WW is going to be the number of columns that we have. and then it's going to apply a fixed voltage at that address. So if we want to perform a NOR between the first two columns to the second to last column, like we see here, we simply give the addresses of these three columns. Now, in order to take this into something that we can support with partitions, which gives us much higher flexibility again, because we're able to both do full parallelism, full serial, and also that semi-parallelism, we designed a technique that we call half gates. And that basic idea of half gates is that we're gonna have in each partition something similar to what you saw on the previous slide. Each partition is gonna have these decoders, and the decoders get 3 addresses and then apply 3 voltages. But we're gonna have some mask that tells us when to apply and not apply voltage. So instead of in the previous slide where we always apply 3 voltages, now we're gonna add in a mask, we call it the opcode. And this opcode is saying when to apply or not apply one of the 3 voltages. Let's see an example here. I'm trying to perform a logic operation with 2 inputs from the first partition, the output in the second partition, and in parallel 2 inputs in the third partition and the output in the fourth partition. So what I can do here is specify for the first partition to only apply input voltages. That's what we see here. In A and in B are coming from inside the partition, so apply their voltages, and don't apply output voltages. Why? Because we trust that a different partition, in this case the second partition, will get an opcode to apply only output voltages. And this is where you're building the logic gate with input voltages being applied in one partition and output voltages being applied in a different partition. This is the basic idea of the half gates technique. On top of that, first of all, this makes it possible from a hardware perspective to support this periphery without needing too many different row decoders to support all the different types of parallelism. The next part we did was try to take a subset of all of the set of operations that are going to be supported with this, all of the different addresses you can supply, and then we define in the paper different versions of those subsets until we get to the most minimal one that on the one hand is able to support all the theoretical operations you saw until now. All operations that we had previously, shift, reduce, broadcast, and prefix are supported completely. And on the other hand, it's able to compress the encoding from approximately 1000 bits all the way down to around 40 bits. And it's taking all of the information that we see here and then compressing it into the representation that you see over here in terms of what are the different bits that we need to represent in terms for that logic operation. So again, more details in the paper for all the different versions that we have and all the different levels of support. But the bottom line is we're able to take the vast space of all possible partition operations you can perform, reduce it in such a way that on the one hand, all theoretical algorithms built until now are still fully supported without any latency addition. And on the other hand, we're able to perform this with a compressed operation format of only 40 bits. So now we're going to move on to our last instruction. It's going to be a move operation. It's going to be inter-array. When you're doing processing in memory beyond a single crossbar, you want to have some inter-array communication. We also talked about it in Geraldo's talk at the beginning. And here we're following an H-tree communication network, which means that the arrays are divided into an H-tree and they can communicate with varying levels of parallelism according to how far the communication needs to reach. So that was a dive into our microarchitecture. Now let's think about how we can take this microarchitecture and generalize it into something that won't be specific to a single chip, but rather builds up towards large operations. And for that, the first question is going to be, how do we perform these larger operations? How do we go from bitwise NOR all the way up to more complex operations? Now, Geraldo also already showed us in his talk how we can do addition. Addition, you can take a full adder, convert it to a series of majority gates or NOR gates, either one works, and then perform them serially in order to get, on the one hand, addition that's bit serial. That means that it's processing each time a single bit of that vector. On the other hand, it's row parallel. It's happening in parallel across many different pairs of numbers, and that's giving you some vectored operation. And that's what we see here on the top right corner. On the top right corner, we have bit serial element parallel. And these are algorithms that their goal is to perform logic within a single row using a single NOR per cycle per row so that you can parallelize it across all rows for vector instructions at the same time. Now, within this model, we have a previous work. It's called PyPIM that takes that model and then defines 4 different arithmetic operations: addition, subtraction, multiplication, division for both fixed point, which we know the state-of-the-art algorithms such as ripple carry, but also extends it to support floating point operations. Now, that is all for bit serial element parallel. The other possibility is bit parallel element parallel. You don't want to perform addition one NOR gate at a time. You want to perform addition with several NOR gates per cycle and still be in parallel across many elements. And that's what's possible with partitions. Because once we have partitions, we're able to perform multiple operations at the same time. So I won't dive in too much into our PyPIM because the previous work of ours was published in IEEE TATC. You're welcome to take a look, but rather we'll ask how can we utilize these algorithms that build from NOR gates to arithmetic, if it is using partitions or without partitions, to something that's more generic. And for that, we're going to try and take a crossbar array, as we're familiar with from our discussion until now, and in fact extract it as a warp. We're taking some inspiration here from NVIDIA's model of CUDA, where they have warps of threads, where each warp of several threads are operating in lockstep. They always perform the same operation. And here we're going to take a crossbar array and think of it as a warp. Instead of rows, we have threads. Each thread is going to be a single row of the warp. Instead of different columns we can store information, each thread has its registers. So for example, if our crossbar array had 1024 columns, so 32 32-bit numbers, here we're going to represent that with 32 32-bit registers. And the interesting part here is that on the one hand, from a parallelism compute perspective, it's similar to CUDA. You're operating with all the threads performing the same operation. You have to operate in lockstep. On the other hand, the warps are the memory. Let me emphasize that a bit more. In CUDA, you allocate warps inside the GPU's processing units. Then they copy data from the memory, bring it to the SM, and then perform operation and bring it back. Here, the warps are also the memory themselves. The registers are the memory. And so what we're going to have to do is think of it more as you're activating the existing warps that are there all across the memory in the region where your data is already stored, and then they perform the computation there. Now, what can we do with these warps? What type of operations do we support? So we support two main types of operations: archetype operations, register operations that take the algorithms we proposed in the PyPIM, generalize them to register operations we can apply here. So we have support for arithmetic, comparison, bitwise, and miscellaneous routines, and move instructions. Move instructions can be move instructions within a warp, and then that's just utilizing operations inside the warp, inside the crossbar, or it can be move operations across different warps, and then that's utilizing the H tree that we saw earlier from the microarchitecture. So the main idea here of the ISA is to take the notion of parallelism and processing memory that we're getting from this microarchitecture and generalize it into something that will apply not only to the FIM chips, but also to other chips in general. And so what we need is some unit that's going to convert between the two. And that's going to be our driver. Our driver is going to get these high-level ISA instructions, convert it to micro operations. And the goal of the driver, it's going to be the driver. And on top of that, we have the Python development library. The Python development library is converting our Python operations to the ISA. And now the goal of both of them is going to be to take very high-level Python operations as we saw earlier. So this can be tensor applications, such as performing a sequence of operations on tensors, a times b plus a, and then that's converted to operations that are performed at the micro operation level, and also support interactive debugging. The idea here of interactive debugging is that because it's Python, you're able to interactively work with the PIM memory. So you can define a tensor, you can write to the tensor, you can get a view of the tensor. For example, here we ask for all the even elements of the tensor. You can sum, you can sort. All operations are going to be supported by, they're already supported by the development library. So for example, when we're doing these operations on the left, all of the a times b plus r plus a operations are going to be converted to regular R type instructions. But then when we get to something more complex like reduction, then that is utilizing a routine that's performing move operations using the H tree, utilizing the parallelism of the H tree to perform these move operations. And then on top of that, adding an algorithm for reduction so that I can do it in logarithmic time. And then it's both saving latency in terms of the copy operations and the addition operations because it's doing it in logarithmic time. Now, the role of the driver is to take these ISA instructions, the R-type instructions, and essentially to convert them to the sequence of micro operations. Again, more details in the paper, but at the end of the day, it's just the implementations of algorithms such as the PyPIM that get high-level algorithms to implement, like addition, multiplication, division, and then spit out a sequence of operations that need to be performed. Okay, so now we've seen all of the proposed parts of the library itself. We're going to focus on how do we evaluate it and how do we simulate it. And in order to evaluate the library, we're going to have three criteria. The first criteria is going to be correctness. we want that whatever we perform in the PyPIM accelerator is going to have the same correctness as CPU. The second is throughput. Now, throughput, we're not measuring throughput compared to CPU or GPU because other previous works of ours have already done that, such as RichPIM or other works such as FourierPIM. But rather, we're just going to measure that we don't have performance degradation compared to regular processing and memory developed on this architecture from all of the libraries we've added in order to increase their accessibility. And the last thing is going to be simplicity. We're going to see some examples of how very complex operations can be reduced to a few lines of code. In terms of parameters, we're giving here a brief overview of the parameters, but it's going to be an 8 GB memory consisting of 1000 by 1000 arrays, n equals 32 and 300 megahertz. Its configuration is based on a recent paper called Racer from Micro. And in terms of benchmarks, we're going to start with very simple benchmarks of arithmetic, comparison, and such. We're going to make it a bit more complex with quartic, sine, cosine. And then we're going to add more complex algorithms, reduction, and sorting, all of them considered in the paper. So I'm going to give a very brief overview of the throughput results. In terms of the throughput results, what we see here is we have the throughput comparison for 3 different types of architectures. We have PyPIM itself. We have theoretical PIM, which is just based on the number of cycles you need to perform these operations. And a theoretical approach to PIM, what is the throughput you're going to get? And the third one is the host driver. Here we want to make sure that our host driver implementation is able to get to throughput that's at least an order of magnitude greater than the theoretical processing and memory, so that it won't be a bottleneck. And then what we see here across the board with all the different benchmarks, we're seeing that the difference between the PyPIM and theoretical PIM throughput is very minuscule. That's because we're not adding a lot of overhead with these operations, with this abstraction that we're adding to the model. And you also have a host driver that's capable of supporting a throughput that is an order of magnitude beyond the throughput of PIM. So it won't be a bottleneck to the overall PIM system. So now here you also see the different benchmarks we have from addition all the way to sorting. And for each one of them, before presenting the throughput result, we verified bit exact correctness if it's floating point or integer operations compared to a NumPy implementation. And in terms of simplicity, what we see here is the implementation of reduction and sorting behind the scenes, what's happening inside the Python library. You could have also done it yourself on top of the Python library. And here, essentially, we're utilizing the ability to perform move operations independently. Whenever you want to perform move operations using the H tree, you only need to specify 2 different addressing. For example, I can say, give me Y all even elements, give me Y all odd elements. And if I request an addition between the 2 of them, the development library on its own recognizes that they're not aligned. It performs a shift operation to align them using the H tree to move data when necessary, and then performs that operation for you. Which means that to perform logarithmic reduction using an H tree in log of n time, all you need is a single for loop, and to do each time an addition with a different function. And to perform sorting, we actually had a work of ours prepared to submit about sorting, and then when we finished PyPIM, we realized that the entire work can be reduced to these 10 lines of code, which is just implementing a Botonic sorting network using these operations that we already have. So again, I had to keep it brief, but further details are going to be in the paper in terms of the evaluation, the simplicity, and you can try it out yourselves today. You're really able to go and just, if you have a GPU, you can simulate these operations with the Python interface. And I'll conclude by saying that we had 3 goals that we wanted to achieve here. The first was the array periphery and operation format, where we focused a lot on how to define that for partition-enabled memoristic processing memory systems. How can you define the vast array of operations you can perform with a compressed data encoding? The second was programming abstraction. We defined this model from the microarchitecture to the ISA. How can we think in a more general fashion about this parallelism that PIM is providing us? And then lastly, accessibility and simulation. We have this Python interface that you can try out today, which lets you almost have a drop-in replacement to libraries such as NumPy and PyTorch, and try out PIM today, see how it can improve your algorithms. Okay, so that'll be all. And I'm here if you have any questions.
All right, thank you very much, Orian, for the presentation. Let me stop the recording and then we can start the